Let people in. Yep. So, hello everyone. Welcome to our Smart MCs monthly webinar. My name is Ling. I'm the CTO of Smart MCs. Today, we're excited to have Associate Professor Khoon Lim from the University of Sydney as our speaker. Khoon is an excellent researcher in biomaterial and especially light-sensitive materials. I will hand over to Khoon now to introduce himself and start the talk. But if you have any questions during the presentation, please feel free to drop in the chat box at any time, and I will share with Khoon during the Q&A session at the end. So now over to you, Khoon.
Thank you. Thanks, Lynn, and Paya. Thanks, Smart MC, for the invitation. Nice to be able to share some of the work that we are doing here in Sydney. So I'm from the University of Sydney. I'm currently at the School of Medical Sciences with the Faculty of Medicine and Health, and I'm also the co-director of the Sydney Biomanufacturing Incubator here. So what I want to talk about today mostly is around some of the different hydrogel-based biomaterials that we have been developing over the last couple of years. We use them for 3D bioprinting, that's our core interest, but we also use them for other tissue engineering and regenerative medicine applications, which I'll talk a little bit about it at the end as well. Right, so if I give a little bit of background of how I got to where I am, I train as a polymer chemist. So my core interest has always been on making different polymers in the lab, looking at different various types of chemistries. How can we make polymers more functional, less functional, for example. And then in my honors years, a lot of the polymers that we make were used to make biomaterials, and that also sparked a huge interest for myself, where designing these polymers in the lab can direct how the body responds to them, or how cells react to them, and I found that really, really interesting. And we're talking about biomaterials, specifically, you use them for tissue engineering. So we were making hydrogels where we can encapsulate cells within them at the start, looking at how the cells would then grow, would then start forming their own, extracellular matrix within them, degrade the material, not degrade the material. I was super fascinating about that. And when I went to the University of Otago, Christchurch in New Zealand for my postdoc, we were then looking at advanced fabrication technology. We now have the polymers, the materials that we know that we designed them for tissue engineering. How can we use advanced biofabrication modalities to now shape these materials? And by shaping the materials, would cells respond to them differently? So this is kind of an overview of where I have been and where I came to now in my research interest. And because I do, fundamentally still around the polymer chemistry and the biomaterials, in my lab, we make a lot of different hydrogels. One of the precursor of interest or the polymer of choice that we use is gelatin. So gelatin, I believe, is not foreign to a lot of people. You can get gelatin from different sources. It can be from bovine, porcine, can be from fish, for example. It's very cheap. And gelatin has all of these beautiful primary amine sites on them that you can easily chemically modify. So as a polymer chemist, we like to take gelatin, we put different groups on them, for example, methacryloyl groups, or we can put allele groups, we can put norbornene groups on them, or you can put both methacryloyls or methacrylamide in this case, along with a tyramine group. So it also offers you this versatility where you can chemically conjugate different kinds of unsaturated ester bonds onto gelatin to make them easier to be fabricated into hydrogels, and with mechanics that you can better control. Now, we also work with synthetic polymers. So in cases where you want your base material to not be biofunctional, to be inert, for example, we work with polyvinyl alcohol a lot. You can modify polyvinyl alcohol with, again, standard methacrylate groups or with tyramine groups. But also lately, the group has moved towards working with biological polymers like silk. You can take whole tissue, decellularize them, so you can make decellularized extracellular matrices, turn them into hydrogels, or you can use whole tissue lipoaspirate, for example, and make them into hydrogels and culture cells within them. So these are some of the materials that my group has been working on. Now, the other thing why we want to modify this gelatin with these different groups is to make them light cross-linkable. So I have been a big fan of using light as a way to form shapes. So this is just an example that you can see a photo cross-linkable hydrogel precursor solution, which is in yellow. And when you shine a Mickey Mouse pattern onto it, you can see where the light pattern hits is where you get the hydrogel. So the areas where you don't get the light, you don't get a gel and they remain a liquid. So this shows that you have a lot of spatial temporal control over this gelation process if you use a light cross-linkable material. And if you spend a lot of time in the lab, like myself, maybe too much time, you can start getting Mickey Mouse to dance on the glass slide, for example. So this is also a prime example of controlling the spatial resolution of this. So when I started my journey in light activated biomaterials, at that time, 2010, I believe, a lot of the photo cross-linkable materials out there use ultraviolet as a source of light to cross-link them. And it really started because photo initiators have been used in paint a lot. So if you have them in paint, if you can imagine just painting a building and then you get a lot of sunlight, the site would then slowly dry out the paint, but also form these cross links to stabilize the paint and the color. So what we then were looking into was, we know that ultraviolet light is not that great for cells. We know that if you have over UV exposure for cells, you potentially will cause a lot of genotoxicity or cytotoxicity to the cells. So can we come up with a different system that absorbs in the visible light region? So the photo initiator of choice that we have been working with is looking at using visible light. It's a ruthenium transition metal complex. You can make gels in the presence of an electron acceptor. In this case, we often use sodium presulfate. You can form these sulfate radicals, and these radicals then can propagate to start different chemistry. So chain growth, step growth, or even diatyrosine crosslinks. In this case, I'm sorry you can't see, but this is two biphenyl bonds, biphenyl bond here. Not meant to be done, sorry. So how did we apply this? We use them to make different kinds of constructs with different kinds of bioprinting technology. So one take-home message that I hope you guys will get from this webinar today, at least, is biofabrication is a myriad of tools. So it's a lot of different tools that can fall under bioprinting or biofabrication. It's a tool and it's not a solution. So when we have a problem, just be aware and remember that biofab won't be able to solve majority of the medical problem, but it's a tool there that will allow you to have better spatial, temporal control and the organizational control over the cells that you want to put into these different materials. So I work with bioassembly a lot. Bioassembly is where you can combine thermoplastics along with hydrogel modules. So you can imagine printing thermoplastics and injecting different hydrogel microspheres within them. We do a lot of lithography work. So lithography where the light actually shines from the bottom. This is your photo cross-linkable material. So if you then have your build plate going down into the bath of your resin and light is shining on them, each time when it's slowly moving up, you're solidifying a layer on top of them. And lithography offers you some unprecedented resolution in this case. You can see really nice structures. And extrusion is one that is the most conventionally used. So most of the labs that works in the bioprinting space would have an extrusion bioprinter, and you're really looking at putting hydrogel material and then exerting pressure. You can push them out. You can form some really nice filaments, and you can stack them as well. And you can also have gradient structures in this case. So when we first look at extrusion printing, this is the work that I've been involved in collaboration with Professor Jos Maura here at UMC Utrecht in Netherlands. And the idea was thinking about an osteochondral defect. So you can imagine if a patient would come and have a osteochondral defect, so the cartilage eroded down to the bone, you can scan it, you can transpose that information to a bioprinter, and you can now tell the printer to print into specific shapes. So you can firstly have a mechanical support. You can have different types of bioinks. So this is a bone bioink. Within the bioink, you have the cells of interest. So it can be mesenchymal stem cells with growth factors of interest like BMP2, BMP7, for example. And you can start printing them in a layer by layer fashion. So you first start with your bone layer, and then your cartilage layer. And even within the cartilage layer, you can have different zones. You can have your deep zone, your middle zone, and your superficial zone. And the idea is to have this where you can then transplant that into the patient. Now, my contribution to this as a polymer chemist is to look at how can we have the bioinks tailored or programmed so that the cells that we put within them will start making the tissue that we want. So in this case, these are the different materials that I've worked with. I won't go through them in detail, but the general idea is to have cells within the cartilage space to make chondro-related tissue. So we want them to make a lot of glycosaminoglycan, high expression of aggrecan, and then the cells within the bone layer can start making bone, but also connected to the vascular supply, because we know that bone is vascularized. So how do we tailor each of these different materials? So I'll give you some examples here. So again, how do we look at these different bioinks? So when you think about bioprinting, right, this is kind of a seminal paper that was put out by Jos Maura's group in 2013 now. And at that time, when we were working on extrusion-based bioprinting, what we do know is that the printing is only advantageous if you can get specific shape out of it, right? Everyone knows that you can mix hydrogel materials, precursors, you can pipette them, and you can crossing them into this. That is quite simple. If it's such a simple process, why do we need to complicate it with bioprinting? Unless bioprinting is going to offer us some specific advantages, right? And in this case, bioprinting is supposed to give you a construct that is identical to what you would have designed. So shape fidelity and then maintenance of the shape fidelity is really important. But unfortunately, if you want a polymer or a bioink to print really well and get really good shape, you often have really high stiffness. And if you think about cell culture, if you have very high stiffness, you are restricting the cells to actually migrate, elongate, or form interconnected networks within them. So if you want cells to be happy in these bioinks, in these hydrogels, you want them to be permissive. So you want to have less cross-link density, less polymer concentration, so you can have all of the oxygen, nutrient diffusion, metabolic waste removal, and also want to give the cells space so that they can spread and elongate. So where the field has set off was like, why don't we just sit at this traditional biofabrication window where we have okay amount of polymer crosslinks for the cells to grow, but also okay control over our shape. So that's where we were working at. And then most recently, we are definitely moving towards these novel strategies where you want to have really, really good shape, but also very permissive environment. So this is just an example to show you a good print would look like. You can print this fiber really nicely. You can stack them. And this is a not so good print where you can see that it forms a droplet at the end of the nozzle. And then if you even try to layer them into different shapes, you can't. So this is a review article that if you're interested, please look this up. It was a very seminal paper in the field back then. Now, why do we like to work with gelatin? So I've mentioned that gelatin has this abundance of primary amine that we can control, we can chemically modify. It is highly cytocompatible. You can dissolve gelatin just in PBS. You can add cells to them because of its water solubility. You don't have to worry about playing around with its pH. And its temperature sensitivity is what we are really interested in terms of bioprinting. So if you heat gelatin, it is a liquid. If you cool gelatin down, it will be a jelly-like structure. So you can just imagine with this syringe, I can control the temperature of the syringe. So I can heat it up to 30 degrees, so it will become a solution. But I can also cool down this base plate to 20 degrees. So the moment this is a solution, you can push it out and then it touches onto the base plate. It will solidify as a physical gel, and then you can start stacking them layer by layer. And this process itself is also quite safe with the cells. And you can see here we have put primary human articular chondrocytes and cultured them up to more than 3 weeks, and the cells stay quite highly viable. So this shear thinning process, or using shear force to push these bioinks having cells within them, is often quite cytocompatible to the cells. So you can start making anatomical constructs like this, for example, of the whole human nose, and that works quite well with gelatin. What we also know is that gelatin itself is not biofunctional enough. So Gabriella, who was a PhD student in our group back then, started looking at, can we make more cartilage prone bioinks? Can we design the materials to specifically support human articular chondrocytes to make tissue? So in this case, Gabriella looked at putting heparin into the gels. We know that heparin can aid with growth factor presentation and regulation, sequestering, for example. And this is quite prominent. So you can see the materials that we do not add heparin, the articular chondrocytes within them can't make tissue. If you now add heparin in them, covalently bound to the hydrogel, culture them up to 5 weeks, you can see abundance more of glycosaminoglycan, as evidenced as the red staining here, that the cells are now producing within this material. What we also found is that you can also control tissue formation based on how you culture these samples. So if you do a normoxic culture, for example, you don't see that much tissue. If you put these samples into a hypoxic culture, you will see a lot more matrix production within this hydrogel. And this really do make sense because cartilage in itself is an avascular tissue. So if you now put your cartilage or your chondrocytes into these hydrogels and then put them into a hypoxic culture, you will see a lot more tissue formation. So we thought that was really nice in making a cartilage bioink. When we then look into making bone bioinks, Caesar here started looking into making strontium nanoparticles. So strontium granulate, for example, has already been used in the clinic. It is being used to treat osteoporosis. So we use strontium as our way to make these nanorods. We again mix them into our gelatin-based bioinks. This time we put human mesenchymal stroma cells within them as we extrude. So you can see that the inks can extrude, you can stack them. What I'll draw your attention to is this bottom panel here, where you can see from day 0 up to day 28, there is a lot more darker dots that are forming on them. And all of these dots are when the MSCs themselves are starting to mineralize. So we stain for calcium deposits within them, and you can see the cells are within the fiber, and within the fiber, they are starting to form all of these mineralized nodules. So the presence of the strontium is there to support the cells to start making bone in this material. When you think about bone though, a healthy bone is technically well vascularized. So how do we then control the bioink in terms of trying to get vascular supply to grow into them? If I want a bone implant to stay long and healthy, sustainable and viable, we need to make sure that you have healthy blood supply into them. What we did found, which was this work done by Barbara, is if you play around with your gelatin-based bioinks and the stiffness of it, we see that a low stiffness, the vascular cells or the endothelial cells are able to form microcapillaries. If you increase the stiffness by a bit, not by a lot in this case, so 1 kilopascal to 3 kilopascal, the cells no longer form a microcapillary and they start forming an endothelium. So the vascular cells are very, very sensitive to the mechanics of the bioinks that we are presenting to them. And then by knowing that, we can start making constructs like this, where you have a channel where you can sit cells will form an endothelium within them. And then you can see in the surrounding bulk, we want the endothelium to be connected to microcapillaries. What we also then found is that these endothelial cells really need support cells, and that's what they do in the native vascular biology. All of these endothelial cells or microcapillaries have smooth muscle cells that goes to stabilize them. So if you co-culture these endothelial progenitor cells along with some mesenchymal stromal cells, you can see the capillaries form, the stromal cells around to stabilize them. And it's also really nice to see that the progenitor cells are sprouting and forming these really nice networks, protrusion, to try to form more interconnected networks within these vascular bioinks. The other thing that we found in terms of printing is also looking at the architecture and how architecture is going to affect vascular formation. So in this case, we're able to print constructs where you have channels of 200 microns all of the way to 750 microns. And you can see here from day 3 to day 7, if you have any open channels that is less than 500 microns, by day 7, you can see that the channels are now already filled with cells, right? And this is quite important because with this vascular formation, often when the cells form these interconnected networks, they would pull the construct together. And if you remember what I said at the front, where, the whole advantage of using bioprinting is to be able to get constructs of specific shape and then maintenance of the shape. But what's really important is that how cells will function within them. So if the cells would come in, although you give them some pause, and then they are going to extend through all of these channels and fully pull and collapse the construct, then you're losing the whole point of printing this material from the very start, because it's just going to be a big hypoxic ball where the cells can no longer survive inside. What we found here is if you use 750 microns, you have less infill into this channel. So perhaps we really need to think about how do we design the porosity within these materials and these constructs so that you don't lose the overall shape when vascularization is a key parameter to consider. What we also found that is interesting is that all of these red colored cells are actually mesenchymal stromal cells. The green here are the endothelial cells. So we see a lot of single MSC bridges. So at day 3, you get these single bridges. So the MSCs are the ones that are forming this pathway or this bridge for the endothelial cells to then come to migrate on them. So by using even simple designs like this, you are able to kind of probe into some fundamental biological questions to how paracrine signaling will happen, how cell-cell communication will happen, in a 3D environment, but also in response to channels or porosity. So this is a paper that is done by Bram and Gretel here, was in my group. Now, that was some of the examples in extrusion. If I touch a little bit on lithography, lithography is an interesting technique, mainly because this technique is very much dependent on light, right? So in order to be able to print with lithography, it needs to be a photo cross-linkable material in this case. So we work a bit on trying to get high resolution print features. So everything that I've showed you in terms of the extrusion, the best fiber diameter that we can get between them is about 200 microns, right? But if you do lithography, because it's very much a voxel printing, you can see here that each of these voxel or these sharp diamonds are at 25 microns. So you're bringing the resolution one step higher. And for prints that you do need resolution, lithography will be a really good choice. And you can make constructs like this where it's big channel, narrow channel, medium channel, all in one. Or you can also print beautiful woven mesh structures like this, where you can have hydrogels weaving in between different hydrogel fibers. And on each of these fibers, you can see an increase in steps. So this is like 25 micron, 25 micron. So now you can add additional surface topology to some of these printed constructs, and cells might respond to them very differently. So that is one of the advantages of using lithography. One thing that we also tried to do is this collaboration with Ricardo and Shrike here, where we look at making different organ-on-a-chip models or microfluidic chip models. So all of these are printed with gelatin. You can make perfusible channels within them. This, I think, is one of the really cool example where it's a truncated blood vessel that we took from a patient's angiogram. So you can see the printing here. If you try to perfuse through it, you can see a bubble form here because the blood vessel is kind of truncated. And these are all open and hollow. So you can perfuse two different kinds of liquids, and you can see from this CT imaging here that both of them are open. And this is interesting because you can continuously perfuse, and you can also look at oxygen or nutrient transfer from one channel to the other channel. And because it's all printed with hydrogels, cells can be encapsulated in the surrounding bulk. So we're bringing quite a lot of different dimensions and parameters into our cell-laden organ-on-a-chip models in this case. Another thing on lithography that I wanted to share was this work that we done with Shrek as well, where we were a bit frustrated that a lot of the materials that we make has to be tested on conventional printers. And of course, a lot of bioprinters are not cheap to purchase. So then we were going down this venture where can we make our own bioprinter, or can we make a bioprinter that is portable and affordable, but also operational through a mobile phone? So we did a smartphone-based DLP printer. So this is kind of what the prototype looks like, how the light will shine through a mirror, and this is where you're going to have your photo cross-linkable material here. And this is the video to show the app that we did with it. So you can have an app, you can print a model, you can say slice the model into different voxels, different layers, and you can see positioning of the build plate. This is where the photo cross-linkable material goes. Light comes from the bottom, and as it prints, you can see each of the layers print out really nicely. And all of this was done and operated with just a smartphone. So we thought that was quite cool. We tried to validate our printer with some conventional resins. So these are resins that you can buy out there. There are a lot of SLA, DLP printers out there, like the Form Labs, for example. So we try some of the resins, we can print them. One thing to note though is there is a reason with the some of the printers to say that they have much higher resolution and they have a longer print time, because print time and resolution normally come hand in hand. So in this case, when we look at the Moe SLA 3D printer, one of the tough resin versus the DLP printer that we kind of made, this took us 16 minutes, this took us 9 hours to print, so same height. But what we also see is this gives us better resolution when all of these open features remain open, but with our smartphone, we don't get that anymore. So it is kind of a balance where if you want the speed, do you need the resolution, right? But also down to the application that you're trying to target. For most applications, perhaps we don't need too much of the resolution. We just need something that is accessible. We tried with hydrogels, so we did standard, polyethylene glycol, diacrylate bioresins, gelatin methacrylate oil, allylated gelatin, and we can print them into these different shapes as well. So we thought that was quite nice, and we did publish this paper too. Right. So that is something that I wanted to show in terms of making these different gelatin-based materials, biofunctionalizing them for different applications, making these bioinks and then applying them to different printing technologies. But remember, most of these bioinks are biomaterials. They started off as biomaterials. We are using hydrogels. We're using standard hydrogels that can be used for a range of tissue engineering applications. So I wanted to also make sure that my second take-home message for you guys is that a lot of the biomaterials can be applied as bioinks and vice versa, right? If you just need a material to do 3D cell culture, there are standard biomaterials out there that you can use, but most of the bioinks can also be applied to do 3D cell culture. So one thing that I'll talk about is some of the work we did in growth factor delivery. For example, we have been designing this polyvinyl alcohol-based delivery vehicle. So we put a tyramine on there. This ruthenium sodium trisulfate system that I kind of touched on at the start it has this really advantageous mechanism where if a protein has a tyrosine group on them or a phenyl moiety, this tyrosine group can form a biphenyl bond or a covalent bond with the tyramine on my PVA chain. So if I mix them, put my photoinitiators, shine light, I form this really beautiful cross-links between them. And because my polymer is degradable due to this ester bond here, as these ester bonds are being cleaved over time, I can slowly release these proteins of interest out from the system. So this is just a gel that I show, and we're using this for controlled release of therapeutics in this case. So we prove that you can start putting growth factors in them. We have an interest in vascularization. So we look at vasculogenic growth factors. So vascular endothelial growth factor, beta fibroblast growth factor, brain-derived neurotropic factor, for example, you can incorporate them. Depending on the concentration of photoinitiators that you use, you can control how much you keep within these hydrogels. So we've looked at that. More photoinitiators, of course, you have more of these growth factors covalently bound within the system. And you can see then when you start culturing them just in media, as the hydrogel itself is slowly degrading, you are releasing the growth factor. So low photoinitiator concentration slowly increasing over time. And you can see that the release profiles goes from about 10 days to 40 days to about 70 days. So very much covalent incorporation, depending on the biphenyl bonds that we are now imparting due to the visible light photoinitiating system. And as the hydrogel backbone themselves is degrading, we are slowly releasing these factors. And by playing around with the degree of cross-linking, we can now tune the degradation or the release profile of these growth factors that we put in there. So we thought this was really interesting, and we did publish this work too. Now, we were looking at translational application. So one thing that we did was for rotator cuff repair. So this is one of the PVA tyramine hydrogel that we added with a cocktail of growth factor. This is a sheep acute rotator cuff surgery. This is where the cuff is. This is where the surgeons then put on our hydrogel, suture it in. You can see that here. And what we did see is at both 6 weeks and 12 weeks, with the hydrogel and the specific growth factor cocktail that we have put in at this time, you see an increase in the biomechanics. So these hydrogels are there, and at both time points, they did facilitate tissue regeneration of the rotator cuff to increase the biomechanics. So they are functional as they are being released from the hydrogels. These gels are also injectable, so that's actually quite cool. So what you see before was just making them into a film where you just put on and you kind of suture, right? But you can also make these gels, and they have these shear thinning properties as well, where you can put them into a syringe and you can kind of just push them, and then they will just inject out quite nicely. So we look at the difference between if you cast them as this or if you put them into a syringe and then inject them out. We don't see a lot of difference between them. We see differences more between if the hydrogel is supposed to degrade faster or slower, but that is really much determined by the amount of cross-linking density that you have within these hydrogels. When we implanted this subcutaneously, we didn't really see any differences in the hydrogel properties on how they interact with the surrounding tissue. So a cast gel and an injected gel, they really look similar. The degree of cell infiltration are the same, depending on the format. But what is different is if the gel is degrading faster, you get more cell interaction or cell infiltration. If it's degrading slower, you have less. And that's understandable. As the gels are degrading, they're opening up more space. And of course, more cells are able to get into the pocket of where the hydrogels are. So this is what we saw. Now, because it is degradable, we also had an application in mind where we wanted to look at avascular necrosis in the femoral head. So avascular necrosis is often when you have the femoral head and the blood supply that is delivering oxygen and nutrient to the femoral head is disrupted. So the femoral head can't grow, it slowly gets necrotic, and then it starts to shrink. If it shrinks, can you imagine the femoral head will kind of just fall off your hip socket, right? So that's not something good. So what we then look into is that if you have a femoral head that is avascular, what the surgeons can do is to drill a hole across here, and we can make our hydrogels in syringes. So this is the gel precursor solution, shine them under light, and then you can put them very easily, just inject into the canal where we've just drilled the hole. So we can use this as a way to targetly deliver the growth factors to the growth plate within the femoral head. So this is kind of just to show what it looks like. So when you drill the hole, you form this tunnel here. This is after you inject the gel. You can see that the gel now fills up this tunnel. This is from side, top view, side view. We have them just to prove that the gels themselves are definitely filling up the canal in this case. And it is really quite amazing to look at the differences in terms of the tissue regeneration, where this is sham, where we kind of just drill a hole and we didn't really treat much. You can see the samples now are slowly shrinking. You can see necrotic lesions now happening within them. This is a healthy control where you see really nice preservation of your femoral head. The cartilage layer stays intact, and then the beautiful porous structure of the bone is still there. And in the gels that we then drill a hole and then inject the hydrogel with the growth factor, in this case, you can see in the treated gels, you also get really nice preservation of the cartilage and also preservation of the overall femoral head shape. So this is showing that the same material, you can mold them into a disc for rotated cuff, but you can also use them as injectable material to deliver it into areas that are harder to get to, and in this case, still deliver the growth factor of interest to then get better preservation of the femoral head. So we thought this was really promising. Now, one of the last example that I just wanted to show is some of the latest work that we have done on injectable fat graft. So at the start, when I spoke about the different materials that my group worked with, I spoke about whole tissue lipoaspirate. The lipoaspirate has been used for autologous fat grafting. So one of the issue is that for breast patients with breast cancer, for example, they often will go through a whole mastectomy. And if they have a mastectomy, the way to surgically reconstruct the breast is to look at either using prosthetic implants or to do autologous reconstruction. And fat grafts has been quite interesting, where you can take lipoaspirate sucked from different parts of the body, and you can inject the fat back directly into the patient. Because it's the patient's own tissue, you should not get quite a lot of graft rejection in this case. So what we look at the time is to say, do we know what is in all of these lipoaspirates? So when you take all of this fat out, what are the different proteins that are in there? So we did LCMS in this case to look at protein fractionation. We extracted them, we look at composition, and we found that a lot of the top hits of the proteins that are detected in the metrosome are proteins that have tyrosine. So you have collagen, laminin, collagen 6 and 4, for example, and all of these are rich in tyrosine. And that is really important for us. What we also found is that there's a lot of different populations of ECM molecules within this fat, and we did look at different patient response, different age, if the fat is taken from different sites, and if it's different age group. We did publish this paper I'll show at the end. So I encourage you to look at this if you're interested to know patient-to-patient variability of lipoaspirates that we are collecting. But this is important to us that they have all of these top proteins that have tyrosines, because with the same technology that I've showed using our ruthenium sodium prosulfate with sublime cross-linking, we should be able to form this covalent dityrosine bond on this protein ECM, right? So you can see here, if you take native fat and then you culture them in media or in water, they will start floating to the top, and then they have no shape on them. But if you take them, mix them with our photo initiators, and then cross-link them, you can see much better preservation of this shape. And we look at the formation of these covalent bonds. We look at how the adipocytes within them and the ECM molecules, if this cross-linking method is going to affect the adipocytes, we don't see any negative phenotypic changes. But what we also did see is increasing our photo initiator concentration. We are increasing the covalent bond formation that are in the native lipoaspirate extracellular matrix. So we thought that was quite cool, because if we form more of these covalent crosslinks, we have much better control over the shape of this native lipoaspirate. So this is just to show that you can now have fat that won't fall. So if you take native fat, 1 mil or 2 mil, you can never stack them up. They would just collapse. But if you now take native fat lipoaspirate mixed with our photo crosslinker and start shining light on them, you can see that even low and medium, you get better control over the shape. So you have increase in the graft shape retention. What we also found is that if you play around with the cross-linking density, because you have better control over it as well, you can now better extrude it. So native fat, if you try to just push it off a nozzle, it kind of just collapses. If you have little bit of photo cross-linking or divalent, this covalent dityrosine bond within them happening, you see better control over the fiber diameter. So you increase the shape integrity. And this is important because a lot of the problems that these patients have is if you take their native fat, unmodified, unprocessed, injected back to them, what normally happens is the fat themselves will form these globules where the vascular supply cannot get into them, and then the injected fat will sort of just die off. It will be reabsorbed back into the patient, and then the patients have to go back to the clinic for a second injection. So what we're trying to do here is to look at controlling all of these mechanics and the shape of the fat so that we no longer need patients to come back for recurring injection. So we did the mouse in vivo study. So this is just taking some of the lipoaspirate and implant them under the skin. And you can see here that the graft looks like that. You know, we just put them into a round cylinder and the vessels are growing into it. We think this is quite cool. So by slowly hardening the fat, we are not stopping the host blood vessels to grow into them. And you can see some of the images here. So native fat, blood vessel can grow into them. Lowly crosslink, medium crosslink, you know, we're demonstrating vascular cell infiltration and also vessel function, because for us to image this, we need to do perfusion into them. So for it to be picked up by the imaging modality, it means that they are open and perfusable in this case. And we also look at migration of endothelial cells to the surrounding grafts, and also red blood cells are able to get there. So this was all really encouraging. What we thought is most encouraging is this, where native fat that are not cross-links, as I mentioned earlier, you can see that they start forming globular structures. So now they're starting to agglomerate under the skin. But if you slightly cross-link it with our visible light photo initiator, you can see better integration with this underlying skin. So what we believe is because the photo initiators can introduce these dityrosine cross-links, on the skin, you should also have some inherent extracellular matrix molecules that have tyrosine. So you potentially are stitching the fat to the skin, so you get much better integration and better shape retention. So what we're trying to do here is to prevent this injection of large lobules that will cause this necrosis, where blood vessels can get to the middle and you're going to get resorption. So we think this is a really promising result, where we're really looking at moving this forward to the next stage. So these are two of the papers that we did publish in this area. Right, so just at the end, I'm just trying to have a disclosure as well, where a lot of this technology is being patented. So we do have a patent on the visible light photo initiators that I've introduced today. We have launched different my screen has just frozen, I'm sorry. Can you guys still hear me? Oh, okay. Yeah. So we have launched, sorry if I go back. We have launched different products over the years as well. So you can also look at some of this bioinks that we have done with our photo initiators. And then just to sum up, I think what I showed today mostly is around different biofabrication technologies and how do we design the different bioinks that potentially can fit these different technologies that are already developed at a very, very rapid pace as well. You know, every 2-3 months, you see a new technology being invented, a new technology being launched, new startup companies. How do we have our bioinks designed to have that functionality, but also adaptable to some of these different printing technologies? Hopefully, I'll demonstrate some of that. And lastly, just have to acknowledge that a lot of this work was done while I was still at the University of Otago. I'm working very closely with Professor Tim Woodfield here, and also my group, and a lot of the different funding agents that have funded a lot of the work over the last couple of years. So thank you very much for joining us today, and I'm happy to take any questions that you might have.
Thank you very much, Khoon. That's a fascinating talk. And every time I come to your talk, you always show me something new. So I'm gonna take advantage of being the host. I will ask my two questions first. And for the audience, please ask your question in the chat now, and then I can pass them to Kun later. So question one is, do you think in the 3D printing process, in the extrusion process, the hydrogel, the cells wrapped inside hydrogel, obviously they are suffering from forces as well. Do you think that's going to make any changes to the cells, or is that kind of like the printing is like too short enough to have an impact?
Um, I think there are quite a lot of different evidence now that the gels are there as a protective barrier for the cells. So in extrusion printing, or even just injection, right? There's a lot of work on just injecting EVs, for example, or cells to targeted sites. And standard injection has too high shear stress that is going to disrupt, the cell membrane and kill the cells, the process. But if you put them in the carrier or within the hydrogel or the bioink itself protects the cells from it, either through force dissipation, firstly, but also cells can bind to specific moieties on these ECM molecules and it stabilize them. So that is being shown quite a lot. Now, functionality is another thing that people have been looking into, like extrusion printing by just pushing them, shearing, and then flowing in the drop. People look at getting cells aligned, at the side. They have showed that it is useful. I don't think I have seen any papers that say extrusion is going to affect functionality per se, but that is for extrusion printing. But if you then talk about like cross-linkable material, we know that our photo cross-linking often is an oxidative. It's a radical mediated process that might cause oxidative damage. So that, I think, has to be checked quite a lot. If you have reactive oxygen species that might actually cause any oxidation-related damage to cell function, but that's yet to have been proven much, I think.
Right, right. Thank you very much. And the second question is, so since hydrogel and biomaterial is such a popular and competitive field, we have seen so many new things coming up like every year all the time. What do you think would be the most critical direction in next 5 to 10 years?
I think depends if we are looking at R&D or if we're looking at getting them into a patient, right? I think regulation takes a long time to get something approved to be able to get into the patient. Now, it is nice that we are making new materials to show new function, but the chances of them getting into a patient will be in 5 to 10 years. So the biomaterials field has been around for so long, way longer than the biofabrication field, I would say. Why not looking at repurposing most of the biomaterials, try to use them in biofabrication, and then you have all of this history of these materials that perhaps it's faster to get into the patient, even through regulations. I think that's what we should be really looking at.
Right. Okay, thank you. So a question from the audience is how do you see the role of droplet microfluidics evolving in the future of biomaterial research? Do you believe it will become a key tool for tissue modeling or other biomedical applications?
I I love droplet microfluidics because I do have an arm of research looking at microfluidics space, fabrication of hydrogels, having cells in them. I think it has a big role. I definitely think so. But droplet-based microfluidics, they can be used for high throughput in vitro tissue models fabrication, but not necessarily needed for bioprinting. I think it goes back, circling back to if we want to print something, is there a need to print something? Or if we want to encapsulate organoids, for example, perhaps a droplet microfluidics based technology will be way easier than trying to put them through a complex printing process.
Right. Thank you. And also a question from Paya. He's asking, um, what do you think the organoids will sit in the future, and how do you see like organ on a chip, uh, like how would it help reducing the animal model usage in the future?
I think it would be really nice if we can make better physiological relevant, organ on a chip models. I believe we are getting there. I really do. What we probably have not really shown for most of the tissues and organs is that our printed constructs or organ on a chip models, they do resemble an animal model. Firstly, right? We need to validate that the things that we are printing now, the things that we're making in the lab, do perform better than an animal, or at least on par than an animal, that we don't need animal studies. Now, the other thing too that is also there is a lot of animal studies that were done, a lot of drugs that were tested on animals, but none of them are translational to a human. So I think if we cannot completely deduce what happens there, then printing or making all of these in vitro models to match animal models to replace them might also then be obsolete. So I feel like there's two kinds of thoughts that we need to really think of in that case. So perhaps not matching what the animals can deliver, but matching what native humans are. But we don't have good human models as well. That's also the other issue, right? Um, and I do see there's a question as well. On if a PhD is essential, both from
Yeah,
Zoe and Paya. I don't think it is. Like honestly, I really don't think a PhD is essential. I think what we're doing a lot is problem solving. I often see the PhD as a way where you get to spend 3 or 4 years working really at the forefront of this technology and really understanding what's happening because biomaterials, biofabrication is moving so quickly, working at the interface, reading all of these papers, going to conferences and all of those to really understand what leading groups are doing in a way is what you're doing in a PhD anyway. So if you're really doing all of these, you must as well get a degree out of it. But if you ask me if it's absolutely essential, I don't think so. I think if you have good problem-solving skills, being able to synthesize the information from the literature, bringing them down, and then carving up what you're trying to make, I think that's completely good or good enough.
okay. Thank you very much. That's quite inspiring. And for the career part, normally we try to, like ask you a few questions about how you kind of like achieve where you are today, and to help the PhD students and early stage researchers get like how to come here, how to go further. And from the question I have, for you is what are the things you regret doing or not doing when you started your career, like when you first finish your PhD and start entering like a university as a researcher?
What do I regret not doing?
Yes.
I would say getting involved in commercialization and getting involved with industry much earlier. I think it is quite nice to actually see where your technology will get to, I must say. And understanding it at a very early stage is good because you can then be designing and developing all of these prototypes, but then get really disheartened when you realize that no one from the clinic will ever use it because it's too complicated, for example. So understanding that is great. The other thing that I would regret is, wouldn't say regret, but coming to a realization that there is a very distinct difference with trying to solve a question to understand fundamental biology just because it's exciting versus trying to solve an existing problem that currently people in the clinic needs help with. And a lot of the incremental changes that we're doing in research can significantly change someone's life, not completely solve all of their problems, but all of these small changes, sometimes it's enough. And for us doing research, we're trying to hit the holy grail, right? You're trying to have the ideal product out there, but it's not necessary. A product that is better than what's currently in the market is good enough. And then you can make more improvements.
Thank you very much. I think that's very true because when I first started our commercialization journey, I always feel like I was being like very naive in a lot of things in terms of like research outcome and like our understanding of the customer's need. I do think, yeah, having that mindset right would hugely impact your research as a researcher, even in the university. And so, another question for you is in a big and competitive organization like UC, can you give us some tips of how to survive inside as a like a beginner, as like a young researcher?
I always say build a peer support network and surround yourself with good people, good supporting people. I think that is very, very important in research in science. Unfortunately, most of the times we are bombarded with rejections, papers being rejected, grants being rejected, investors not wanting to put money into stuff. Like we have so much rejection, so many rejection. But if you're surrounded by good people that are there to continuously uplift you, all of these rejections are less of an impact to you. And I think not really just in USAID, I think mainly in life or in anything that we're doing, just make sure you have a group of people you can always rely on, and they would be your cheerleaders, and they would always help you through once you get something your way, which is not expected, and things that you do not want in your life or do not hope to ever have in your life.
Yeah, yeah. Okay. Thank you very much. That's very inspiring. And so I guess now it's about like 7 p.m. in Sydney. I should let you go. And let's wrap up the talk today. Thank you all for joining us today. And if you'd like to revisit this fantastic talk, the recording will be available soon on our Smart MCs YouTube channel. And a big thank you again, Khoon, for sharing your time with and insights with us. And wish everyone has a great weekend. Thank you very
Thank
much.
you. Thanks, Lynn. See you,
Right.
everyone.
See you. Bye.